Hi everyone, I'm Sungyeon Kim from KAIST Graduate School of AI. This is our paper, Self-Contrastive Learning, Single-Viewed Supervised Contrastive Framework using Subnetwork. This is joint work in collaboration with Sangmin Bae, Jongwoo Ko, Ki-Hyun Lee, Seung-Jong No, and Seyoung Yoon. First, let us briefly summarize the main idea of our paper. In this work, we propose self-contrastive learning, which self-contrasts within multiple outputs from the different levels of a single network. So now I'm going to explain what is self-contrasting and why we need this. We focus on supervised contrastive learning tasks where label information is given and the same classes imply positive samples. This supervised contrastive learning has been developed on the top of a multi-viewed framework. So multi-view can be thought of as augmentation of the same sample or same image. So in the figure, you can see the anchor and positive pair, which are augmentations of the same dog images. Multi-viewed framework therefore leverages augmentation and label information when formulating the contrastive task. However, the multi-view approach makes the training time and memory usage highly expensive because it basically requires more samples to train. So what we propose is self-contrastive learning that self-contrasts within multiple outputs from a single network. And this is to implement the multi-view framework without data augmentation. We drew a nice picture to describe what SubCon is doing. SubCon is a single-viewed supervised contrastive learning framework that produces multiple features from a single instance using the subnetwork. So in the figure B, SubCon represents a single image onto different space featured by the original backbone and an auxiliary subnetwork. This is the short summary of our paper, and now let's figure out how this works. First, what is supervised contrastive learning? As I briefly introduced, the idea of supervised contrastive learning, or SubCon, is to make representations from the same class closer together and representations from different classes farther apart. We call the instances that become close positives and the instances that become far apart negatives. The loss function looks quite complicated, but it's just similar to cross-entropy loss that predicts which is the positive sample among the negatives. And what is the multi-exit architecture? As earlier layers of the deep neural network suffer from the vanishing gradient issue, previous works have introduced a multi-exit architecture that attaches subnetworks on the intermediate layers. Recently, the knowledge distillation-based losses have been proposed to effectively train the subnetwork. And motivated by these methods, we propose a novel supervised contrastive learning that self-contrasts within the multi-exit outputs. SubCon still uses the multi-viewed batch, even though there is a usable label information. The diagram describes how SubCon formulates a contrastive task. We can see the yellow one, anchor, and the green ones, positives. And not only the same class cat images are the positives, but also the augmented images are positives. However, SelfCon does not use data augmentation-based multi-views. Actually, SelfCon eliminates multi-views and forms a self-contrastive task for every output, including the features from the subnetwork. So we can obtain another positive feature from the same image by using the subnetwork. And this is the visualization of self-con loss. Note that the subcon loss has the same form as self-con, but uses the representations from the multi-viewed batch. In the loss function, the large omega is a function set of the backbone network and the subnetwork. Whereas prevalent contrastive approaches such as subcon force a multi-viewed batch generated by data augmentation, the subnetwork in self-con learning plays a role as the augmentation and provides an alternative view on the feature space. Therefore, without the additional augmented samples, we formulate our self-con loss function with a single viewed batch. In the paper, we also provide a mutual information bound for subcon and self-con, and theoretically demonstrate that self-con learning improves the classification performance by encouraging the intermediate feature to have more label information. And for the details, please check the paper. To demonstrate the self-consistency effect, we measure the classification accuracy of the representation learning protocol, which consists of two-stage training. First, pre-training an encoder network, and second, fine-tuning a linear classifier with the frozen encoder. We also have implemented subcon with a single-viewed batch, subcon S, and self-con with a multi-viewed batch, self-con M, in order to examine the independent effects of the single view and the subnetwork. So the classification accuracy in the small-scale benchmark is summarized in this table. Self-con learning, which trains using the single view and the subnetwork, shows higher classification accuracy than the cross-entropy and subcon. And the classification accuracy in the large-scale benchmark is summarized in this table. Self-con uses single view, so it is much more efficient than subcon or self-con M, which use multi-viewed batch. Also, the poor performance of subcon S, which consumes an amount of memory and time similar to self-con, reflects the superiority of self-con. And self-con outperforms subcon on both ImageNet 100 and ImageNet. Furthermore, the co-trained subnetwork is a novel strength of self-con as an efficient and simple boosting technique. Ensembling two predictions of the backbone and subnetwork is the most powerful technique we have proposed. In particular, self-con can achieve a significant performance gain of plus 3% on ImageNet without requiring cost-intensive techniques such as multi-viewed batch or larger batch size. Self-con also outperforms subcon in fine-grained recognition and semantic segmentation and object detection tasks. Now let's compare single view and multi-view and why the single view is better. First, single view reduces generalization error. If you look at the blue bars and red bars, subcon shows higher train accuracy but lower test accuracy than subcon S. And the same trend is observed with self-con M and self-con. Second, single view is efficient in terms of memory usage and computation cost, although self-con requires the additional parameters due to the subnetwork. Its memory and computation costs in practice are much more efficient. Next, what does the subnetwork achieve? Our first achievement is regularization effect, just like the regularization effect of the single view. Self-con loss regularizes the subnetwork to output similar features to the backbone network. And this prevents the encoder from overfeeding to the data, and it is effective in multi-viewed as well as single-viewed batches. A second, subnetwork mitigates the vanishing gradient issue. Compared to subcon, self-con learning sends more abundant information to the earlier layers through the gradients flowing from the subnetworks. Finally, subnetwork provides feature-level multi-view. Self-con learning relaxes the dependency on multi-viewed batches. This is accomplished by the multi-views on the representation space made by the parameters of the subnetwork. And here is the conclusion. We propose self-contrastive learning, which is the first study on a single-viewed contrastive framework exploiting multiple features from different levels of a single network. Self-con learning efficiently achieves higher classification accuracy for various benchmarks compared to cross-entropy and subcon loss. We analyze the success of self-con learning by exploring the effect of single view and subnetwork, such as the regularization effect, computation efficiency, or ensemble prediction. As a takeaway, self-con could be an intriguing feature work in that auxiliary networks could be an efficient substitute for data augmentation. So that concludes our presentation. If you are interested, please check out our full paper and feel free to visit our poster at the AAAI 2023 in-person and virtual venue. Email us if you have any questions. Thank you for tuning in.